Hello everyone and welcome to this presentation. My name is Tran-Huy from Phenica University, Vietnam. Today I am going to present our research paper entitled Single-Layer Compact Dual-Band Antenna with High Front-to-Back Ratio for Multi-Service Wireless Applications. This work was co-authored by Cuong Do-Manh, Trang Hoang-Thu, Tran-Huy, and Nguyen-Viet. The primary engineering challenge we address is maintaining a strictly single-layer profile while securing stable broadside gain and suppressing backward radiation, which is critical for minimizing interference with adjacent electronic components. We will begin by reviewing the structural outline of today's discussion. The presentation is organized to logically follow the development and validation of the proposed antenna structure. Initially, the core motivation and the specific limitations characterizing current dual-band solutions are established. Following this, the precise geometric configuration of the antenna is detailed, alongside the fundamental capacitive loading mechanism responsible for the achieved miniaturization. The discussion then proceeds to the quantitative simulation results, evaluating impedance matching, the generation of the dual-band response through surface current perturbation, and the resulting far-field radiation patterns. Finally, the presentation concludes with a summary of the performance metrics and the structural advantages of the proposed design for integration into modern wireless platforms. As modern wireless devices shrink, there is a critical demand for compact antennas capable of simultaneously supporting multiple frequency networks, such as sub-6 GHz, 5G, and Wi-Fi 5.6. While traditional dual-band designs achieve this by vertically stacking multiple dielectric layers or resonators, these bulky, multi-layer approaches are increasingly unsuitable. They significantly increase the antenna's overall thickness, elevate fabrication costs, demand highly sensitive manufacturing alignment, and degrade overall radiation efficiency through increased dielectric loss. A single-layer radiator is the optimal structural candidate for integration into modern thin wireless platforms due to its low fabrication cost and minimal vertical profile. However, engineering a single-layer structure to perform multiple complex functions simultaneously presents a significant electromagnetic challenge. The difficulty lies in balancing four competing factors. The physical footprint must be minimized for compact integration. Within this restricted geometry, the structure must be forced to resonate at two clearly separated frequency bands. Crucially, modifying the geometry to produce this dual-band response frequently degrades the radiation characteristics, yet the design must maintain a stable broadside gain and suppress backward radiation to achieve the required high front-to-back ratio. The proposed design successfully eliminates the need for stacked parasitic elements conforming entirely to a single-layer architecture. The radiating aperture is constructed from four identical square patches distributed symmetrically. Rather than using a complex feed network, these primary radiators are excited completely through capacitive coupling across a narrow physical gap from a centrally located probe-fed patch. To generate the dual-band response without expanding the volume, four discrete L-shaped slots are etched into the square patches, effectively splitting the fundamental resonance. Furthermore, the inherent capacitive loading introduced by the narrow coupling gaps significantly increases the effective electrical length, yielding a 24% reduction in the necessary physical dimensions of the patches compared to theoretical models. The fundamental layout relies on a central, narrow, rectangular patch fed directly by a standard coaxial probe. This central element is designed solely as an exciter. It does not contribute directly to the far-field radiation. Instead, it capacitively couples radio frequency energy across the narrow separating slots into the four surrounding square patches, which form the actual radiating aperture. When these square patches are solid, the structure functions purely as a single-band antenna. To introduce the second operating band, L-shaped slots are embedded into each of the four patches. Maintaining rotational symmetry in the placement of these slots is imperative to ensure the radiation pattern remains stable and directed broadside across both operating frequencies. According to antenna theory, an isolated square patch edge should equal half the effective wavelength. For a 5.1 GHz resonance, the theoretical dimension is 15.7 mm. However, our optimized design reduces this to just 12.5 mm, achieving a 20.4% size reduction. This is possible because the intense electric field across the narrow gaps between patches stores additional reactive energy. This supplementary capacitance effectively increases the radiator's electrical length. Consequently, the target resonance is met using a physically smaller footprint. The dual band response relies entirely on surface current perturbation. A reference solid patch configuration only exhibits a single resonant mode near 5.1 GHz. By embedding L-shaped slots, we physically obstruct and reroute the original symmetrical current paths. This disruption splits the single mode into two distinct operational frequencies. The lower 456 GHz band uses an elongated path tracking the slot's perimeter. Meanwhile, the upper 5.6 GHz band is excited by currents taking a shorter direct diagonal path across the patch surface. Simulated reflection coefficients validate our dual band approach. The slotted design generates two distinct, highly matched resonances, both plunging deeper than 18 dB. The resulting 10 dB bandwidths are 4.47 to 4.60 GHz for the lower band and 5.58 to 5.79 GHz for the upper band. These ranges easily satisfy requirements for targeted sub-6 GHz applications. Importantly, adding these slots does not degrade radiation efficiency. The broadside gain remains remarkably stable at approximately 6.0 dBi across both operating bands. Analyzing vector distributions confirms these operational mechanics. In the unslotted reference antenna at 5.1 GHz, currents align vertically across all four patches. In our proposed design at 4.56 GHz, current density concentrates heavily along the embedded L-shaped slots, physically lengthening the electrical path to lower the frequency. At 5.6 GHz, the vector field shifts, flowing predominantly along the unslotted diagonal axis of the patches. This proves the slot introduces an independent secondary resonant path. Crucially, it does so without disrupting the phase synchronicity required across the four-patch aperture. The simulated far-field radiation displays highly directive behavior at both frequencies. 2D and 3D plots show a dominant main lobe directed broadside. Crucially, backward radiation is intensely suppressed. This yields a high front-to-back ratio exceeding 18 dBb for the lower band and 20 dBb for the upper band. The slight high band asymmetry is due to perturbed diagonal currents but doesn't negatively impact performance. This exceptional front-to-back ratio is vital as it drastically minimizes electromagnetic interference with the physical mounting platform and surrounding device circuitry. To summarize, we successfully designed a highly efficient single-layer dual-band antenna. By engineering narrow gaps between the feed and radiators, we introduced capacitive loading that substantially miniaturized the antenna's footprint. Strategically placing L-shaped slots perturbed surface currents, bifurcating the standard resonance into stable 4.56 GHz and 5.6 GHz operating bands. The final architecture maintains a stable broadside gain of approximately 6. 0 dBi alongside exceptionally high front-to-back ratios. This robust, low-profile configuration is a highly viable candidate for integration into next-generation sub-6 GHz 5G and Wi-Fi 5.6 communication systems.